In the first example in this video, we're given the graph of g of x, and we're asked to identify its domain. Remember, when you're given a graph that does not have any clear endpoints like an open or closed dot, you are to assume the graph goes on forever. And not only is it the case that this graph goes up forever, it also means this graph goes to the left forever. You are to assume that there's no such thing as sort of a wall that the graph is trapped within. If there were such a wall, it would be drawn on the graph. This is also the case to the right of the graph. There's no endpoint here, so you are to assume not only does the graph go up forever, it also goes to the right forever. So remember, the domain is any x value that you can give me, and I can find a point on the graph that has that x value. It is very clear on this grid that there's no open circles or breaks in the graph. So if you gave me an x value of, say, 3, it'd be very easy for me to identify a point, like this one here, whose x value is 3, so 3 would be part of the domain. It'd be very easy to find such a point on the grid. The difficulty is this graph goes up and to the right forever, up and to the left forever, and we are just drawing a finite picture of it. So if you asked me if x equals 6 was in the domain, you would just have to use your imagination and realize that the graph eventually would go to the right far enough, it would be way up here somewhere, that would have an x value of 6. And that argument continues forever to the right. I could eventually find a point on the graph whose x value is 7, 8, etc. Going on forever to the right in the positive direction is usually indicated by the symbol infinity. So just for explanation purposes, I will draw an infinity over here. And then a similar idea would be if you were to talk about a graph going to the left forever, its x values would go forever in the negative direction, which I will refer to as negative infinity. So a fancy way of saying that I can find a point on a graph for any x value you give me is that the domain is all real numbers. It includes everything between negative infinity and infinity. So I write the symbols negative infinity, comma, infinity, since I'm asked to give my answers in interval notation. Because infinity is a concept, not a real number, you never find a point on a graph that has infinity as an output. We indicate that infinity is not included by putting parentheses. The second part of the problem asks, when is the function g of x 0? And when we say when a function is 0, we're talking about its output or its y value. So recall that a point on g of x could be written like this. The x value I'm going to label x, which you would normally call y. We now are in the habit of using the function notation g of x. So when you're asked the question, where is g of x equal to 0, you're actually saying, give me a point on the graph whose y value is 0. Well, if you're a point whose y value is 0, you are on the x-axis. So for example, here is a point, negative 4 comma 0, and that means that when x is negative 4, the output of the function g of x would be 0. So x equals negative 4 is one of the answers. You can also see the x-intercept here, whose x value is negative 1, this x-intercept when x is 2, and this x-intercept when x is 4, would all have y values of 0. So my answers are negative 4, x equals negative 1, 2, and 4. Identifying where a function is 0, in this case these 4 points, helps us answer questions like where would the function be less than 0? So let's talk about that. Now notice in the first question it says, over what interval is g of x strictly less than 0, which means we are not concerned for when the graph actually is equal to 0, and we just pointed out that happens at these 4 values. So since we're not interested in when g of x is 0 this case, because there's no line here, what I will do is put an open circle to indicate that these are 4 important values to this question, but they cannot be included in the solution because these are not the points whose y values are less than 0. In fact, these are the points whose y values are equal to 0, but they help me answer the question. As soon as I draw those 4 points, it's helpful to think that I just broke up this graph into 5 different regions. In your mind at least, visualize this graph being broken up into 5 distinct regions. We have the region to the left of this red dotted line, and everything I just shaded there would have points whose x values are less than negative 4. So what I'm doing now is building the pieces to my answers for the next 4 questions in this problem. My answers will include intervals such as the interval from negative infinity up to x equals negative 4, but I won't include negative 4, remember, at least for the first question. And then this second region here all have x values between -4 and -1. The next region on the graph that these x values break it up into is from -1 to 2. All the points in here have x values between -1 and 2. The fourth region here has x values between 2 and 4. So some of my answers will involve the interval 2 to 4. And then finally we have the part of the region on the graph whose x values are bigger than 4. That would be here. Anything in this region would be considered the interval from 4, and then remember this goes to the right to infinity. So the 5 regions on the graph that I just indicated, and do remember that a couple of those intervals are actually infinite to the right and infinite to the left, that each of these can be written as one of these intervals that I've written over here to the right. Now I cleaned things up a little bit just for the purposes of answering this question. Now here's the easy part. My first question says, where is the function less than 0? We've already identified these open dots to be where the function is equal to 0. And remember that g of x is the y value of the point. So we're saying what points would have a y value that are less than 0, meaning negative. That would be any point on the graph that's below the x-axis. All of these points here that I'm shading in purple are points below the x-axis. And if you went to the right, you'd see their y values are all negative. And those points lie in this region that we labeled from -4 to -1. So this part of the graph here is in this region between these two red lines. And whenever you're in this region, remember, your x values are between -4 and -1. So what I've just highlighted in purple corresponds to this interval right here. It's also very clear that there's another place where the graph is below the x-axis. That's between x equals 2 and x equals 4. Remember, anything in this region on the graph has x values between 2 and 4, and that's where this part of the graph exists. So my answer will include this interval here between 2 and 4. So let's see. The answer to this one would be from -4 to -1. That was this part of the graph. Then the other place the graph was below the x-axis was between 2 and 4. And when we have two intervals that we want to put together, we put a capital U to indicate the union between those two intervals. And having this answer really helps answer the next part where the question asks, where is g of x less than or equal to 0? Which would be the same exact places we've already indicated in purple where the graph has y values less than 0. And earlier we said where g of x is equal to 0. It's equal to 0 at each of these x-intercepts. So because this time we are including the points where g of x is equal to 0, these would be closed dots. And we indicate in interval notation that those dots are included by using a bracket instead of parentheses. So our next answer is literally exactly the same, except we use brackets around all the numbers to indicate that -4, -1, 2, and 4 are all x values that are included in the solution, because those are the x values that make the function, or the y values of the points, equal to 0. For the next part, I turned the circles back to open circles because it's asking where are the y values of the points strictly greater than 0. So I'm not going to be including those 4 numbers because that's where g of x is equal to 0. The graph would have y values greater than 0 wherever you have positive y values. That's everywhere else on the graph. So if I trace over the part of the graph where the graph is above the x-axis, I basically get the other 3 of the 5 intervals that are over here. In fact, if you could think of these 5 intervals put together as basically all real numbers except for those 4 points, because we used parentheses here. So we've already used this interval and this interval. These are the 2 intervals where the graph was below the x-axis, meaning the other 3 intervals here, here, and here are where the graph is above the x-axis. And you can see that it's true. The first portion of the graph I shaded in black here would be this portion whose x values are to the left of -4. That's this interval right here, -infinity to -4. This part of the graph here is where the graph was above the x-axis, and that happened in this region of space between -1 and 2, which is this interval. And finally, the graph is above the x-axis right here, which is in this portion of the graph whose x values are 4 and bigger, and you can just imagine that going to the right forever to infinity, and that is this interval, 4 to infinity. So I need to copy these three intervals down, put a union symbol between them. That's where the graph would be strictly greater than 0. So -∞ to -4, put a capital U for union, -1 to 2, and then another union symbol, and finally from 4 to infinity would be my third interval. And you may guess what the last answer is going to be. They simply changed the problem from being strictly greater than 0 to greater than or equal to 0. So if you're going to allow the function to actually be 0, that would be those 4 points whose x values are -4, -1, 2, and 4. So we have the same answer as before, except we are including those 4 numbers. So I'll copy down the same solution. The graph is above the x-axis or on the x-axis over the same region, except I use brackets around any of the numbers, -4, -1, 2, and 4. And remember that you never use brackets near infinity or -infinity. So I'm just putting brackets near the 4 x values that represent the x-intercepts on the graph for which the function g of x is actually equal to 0. Now let's do a couple more problems for more practice. In this example, we have a graph that fits on this finite grid because we have a clear endpoint here at this closed dot and a clear endpoint here at this open dot here. So my domain will not include infinity. It's trapped between a couple x values. In fact, let me draw some dashed lines to indicate that the graph literally is trapped between x equals -1 here, and it's trapped on the right over here at x equals 3. So all my points exist in this region of space in here, whose x values on the real number line here start at -1 and go to 3. So when I write my domain, I'll write -1, 3. But because this was a closed dot over here, that indicates that x equals -1 is included in the domain, that there actually is a point whose x value is -1. And the open dot here indicates that you get points whose x values are like 2.9999, but never actually hit 3. So we will not include the 3, and we indicate that by putting a parenthesis. So in interval notation, this would be the domain of the function h of x. Next, we're asked, where is the function h of x equal to 0? And remember what that means is we're looking for the x value so that the output, or the y value, now called h of x, is 0. So I'm looking for the points on the graph have the structure some x value, 0. And like before, if you're a point whose y value is 0, you are an x-intercept. So let me clear this away. So at this point, x is 2, and my output h of x is 0. So we know h of x will be 0 when x is 2. The next part asks, over what intervals is the function less than 0? For that problem, I need to change this dot here to an open circle, because that's where the y value is 0, and we are looking for where strictly the y value is less than 0. And I can just shade the part of the graph whose y values are less than 0, meaning they're negative, would be this part of the graph from here to here, and I wouldn't include this point because it's an open circle. So just remember that this open dot here and this open dot here breaks the region up into this small region. This is the part of the grid where the graph is below the x-axis, and it's strictly between x equals 2, which is covered up right here, and x equals 3. It's helpful to think that any points that would be in the yellow shaded region would have x values between 2 and 3. And that's exactly the part of the graph that's below the x-axis. All these points have x values in this yellow shaded region whose x values are between 2 and 3. So I will write 2 and 3, and I'm going to use parentheses because both endpoints were open dots. The next part is very similar. They changed the question so that we are including any points whose function values or y values are equal to 0. That line there indicates we're considering when the y values are equal to 0. And there's only one point whose y value is 0. We said it before. That's this guy right here, when x is 2. So we'll have the same region, except we need to include the 2 by putting a bracket next to the 2. And remember, we'll leave that as a parenthesis around the 3 because this is still an open circle. The next part asks, when is the function strictly greater than 0? Greater than 0 means that the function or the y values are positive. The y values are going to be positive, and that happens above the x-axis. And this is the part of the graph that's above the x-axis. And it's helpful to think again in terms of left and right. The farthest that my purple shading goes is right here at this red dotted line. And the furthest to the left it goes would be this area here, whose x value is -1. And bear with me, my software just messed up and made me redraw everything from scratch. So this is roughly what was on the screen before. And I'm trying to point out that every place on the graph that I just highlighted in black here would have points that are above the x-axis. And then that seems to happen in this area of the graph here, whose x values are between -1 and 2. And then since we're not considering any points whose y values are actually equal to 0 yet, I put an open dot here. So we'd say that we're looking at the part of the graph between -1 and 2, but not including the 2. So my answer will be that we're looking at x values between -1, and we'll include -1 because of that closed dot right there. And we want all x values between -1 up until you get an x value of 2. And we're going to exclude the 2, not include it, by putting a parenthesis there, because at x equals 2, the function is actually equal to 0, and we don't have that line here saying that that counts in this part. In the next part, since they're including points on the graph whose y values are equal to 0, we would just add to the answer that one point whose x value is 2, and we would include the 2 by just changing this parenthesis to a bracket. So the answer would be exactly as it was before. The graph is above the x-axis in this region that I've shaded in yellow between -1 and 2, and this time we include both the -1 and the 2. Let's do one final example. The first question is to identify the domain. This is where I point out, since there's no endpoint here, it goes not only up forever, but to the left forever. Same goes on the right. There's no endpoint, so we are to assume the graph goes to the right and up forever. So if you're used to me shading the graph, the points on this graph that you can see are between about -1 and 5. But since we're to assume that the graph goes to the left and right forever, even though we've drawn it in this finite region, the graph actually goes to the right forever. And the fact there's no dot here means that the graph goes both up and to the left forever. So basically, this is just a fancy way of saying that everything counts. And even though this is a two-dimensional graph, when we say left forever and right forever, we're talking about values on the x-axis. So all x values to the left forever to -infinity, and all x values that go to the right forever to +infinity would be represented by this graph. Meaning any x value you gave me, like 6, I could go up and eventually find a point that hits that x value. You would just have to extend the graph in your mind far enough to convince yourself that it would eventually reach a point whose x value is 6, or 7, or 8, or 9, etc. So the domain is going to be all real numbers from -infinity to infinity. And again, you do not ever include infinity in your answer, and you indicate that by using parentheses. The next part asks, where is the function strictly greater than 0? So to identify where they are greater than 0, I first identify where they're equal to 0, but I'm not going to include them because there's no line here. And it looks like my x-intercepts here are at 0, 0 and at 4, 0. So when x is 0 and when x is 4, we get y values that are 0. But we want where the graph is strictly bigger than 0. So that would be anything where the graph is above the x-axis. These are all points whose y values are positive or greater than 0. And this part of the graph over here also has points with positive y values. Or you can think of it as it's where the graph is above the x-axis. And don't forget that it goes on forever in both directions. So when I identified those x-intercepts, if you let me draw these vertical lines, just to visualize that those two x-intercepts break the space up into 3 distinct regions. And the first region of interest is where the graph is above the x-axis. That happens in here, where all my x values are less than 0. So even though the graph is way up here, we report the interval in terms of the x values on the x-axis, which is right here. So this is the part of the x-axis where the x values are strictly less than 0. Don't forget this goes to the left forever. So this piece of paper, if you will, goes to the left forever and right forever, and there's 3 distinct regions. One is this region right here, which we represent as being the interval from negative infinity up to x equals 0. So I'll write negative infinity and 0. We never include negative infinity. Since we don't want the y value to actually be 0, we exclude this x value here of 0 because that's where the y value is 0, and we want where the y values are strictly greater than 0. I'm going to union that with the other region in space, which is over here, and don't forget that I assume this graph goes both up forever and to the right forever. So the graph would go to the right forever, which I'm going to indicate is positive infinity. And that interval starts with an x value of 4. So on the x-axis, starting at 4 and going to the right forever, we used to just write x greater than 4. But in interval notation, that would look like 4 comma infinity. Never include infinity, put a parenthesis. And again, we're not including x equals 4 because that's where you get a function value of 0, and we are interested only when it is bigger than 0. But in the very next part, of course, they draw the line saying, what if we include the points whose y values are 0? We would have to include x equals 0 in our solution and x equals 4 because those are the points whose y values are actually equal to 0. And that would be very easy to include in our answer. All we would have to do is use brackets next to the 0 and next to the 4 to indicate we're including those x values. Now for the next part, we're interested in finding the interval for where the function values or outputs of the function are strictly less than 5. So whereas we were looking at the x-axis before, which is where points have an output or a y value of 0, we need to look at a horizontal line that would represent where you have function values or outputs that are 5. So at least in your mind, you need to identify where the graph would have a height of 5. I would just draw that as a dotted line through 5. And let me indicate that it's this point on the graph and this point here on the graph that would have a output or a y value of 5. We want to know strictly where is the graph below those points, because any part of the graph below those points would have outputs or y values smaller than 5, and that's the question. Where are my outputs or my y values smaller than 5? So at least visually we see that it's this part of the graph that I'm highlighting now that is clearly below my red dotted line. And as I've done before, if I was to draw a vertical line down from my point of interest, I see that that point has an x value of about -1. And if I were to draw a vertical dashed line from this point of interest, I would see that that point of interest has an x value of 5. So the part of the graph that I've shaded in purple here that is below 5, you can think of exists between these two blue dotted lines. And looking down here on the x-axis, you see that that would be the location where points have x values between -1 and 5. So when we write the interval -1 comma 5, although this looks like a point, we're actually describing this whole region in space, which I've highlighted in yellow, that is trapped between the x value of -1 here and the x value 5. And I put parentheses around the -1 and 5 because these were open circles. Those are the two x values for which the y value of the graph is 5, and we're trying to find where it's strictly smaller than 5. And the next part, we ask where are the function values, or outputs, or y values bigger than or equal to 5. And the part of the graph who has outputs bigger than 5 would be where the graph is above my red dotted line, which is here and to the right over here. But since they have the line indicating that we also want to include when the y values are 5, we should change these to closed dots. So when I drew these two vertical dotted lines, it broke the space up into 3 different regions. One of the regions being between -1 and 5, which was the answer to the last question. Now I'm going to highlight the region of the graph in purple, this region, which actually is an infinite region, it goes to the left forever, because I assumed that my graph went up and to the left forever. So everything to the left of this blue dotted line, everything to the left of -1, would be the region in space where my graph is above the line 5. That's part of my solution, and we write our solution in terms of x values. So how do I say that all the points in the purple region here have x values to the left of -1 or smaller than -1? In inequality notation, we'd say x is less than -1. But in interval notation, we say this goes to the left forever to -infinity. So from -infinity up to -1, and I'll put parentheses around infinity, and since we're including the -1, I will put a bracket, because at -1, that's where the graph had a point whose y value was equal to 5. This is the interval, or one of the intervals rather, where the graph is above y equals 5 here. But we also need to include the region over here, where the graph is above my dotted line, representing y values that are 5. And remember that the assumption is the graph goes not only up, but to the right forever. So this third region in space, which goes to the right forever, would be the region whose x values start at 5 and go to the right forever. So we'd normally write x bigger than 5, that starts at 5 and goes to the right forever to infinity. Again, always put a parenthesis around infinity. I'm including the 5 by putting a bracket, because when x is 5, you actually get a y value or an output of 5. In fact, this point here is 5, 5. And we have two intervals in our answer, so we union them by putting a capital U. I should clear all this because the next question has nothing to do with outputs of 5. They changed it to where the function values or the outputs would be strictly smaller than or less than -3. So I will start by identifying points on the grid whose y value would be -3. That would be any of the points I'm drawing here, and I'm dotting it. And the points on my graph that have y values of -3 are here and here. And I'm interested in what those x values are. We know the y values of the outputs are -3. What would the inputs be? You could find that answer by going up and noticing that this has an x value of 1, and that this point right here, whose output is -3, has an input of 3. It may be helpful to think of this point as 3, -3, and this point being 1, -3. So these are the two x values on my graph that gives me an output of -3. We want to know when the graph is strictly below that line. But as soon as we identified those two key points, you could think of it as we broke the region up into 3 pieces. Anything to the left of this dotted line is one region. Things between the two dotted lines is a second region, and things to the right of this dotted line is a third region. And it turns out our solution is only one of the 3 regions, because we're looking for this part of the graph where the points are below the red dotted line. These would be points below -3, so their y values would be strictly smaller than -3. And anytime we're trying to describe this region in space, we look at the x-axis and we just look at those x values here between 1 and 3 to indicate this yellow shaded region. So the part of the graph, in this case purple, that I'm trying to indicate is in this region that I've shaded in yellow, whose x values are between x equals 1 and x equals 3. So I'm going to write my answer as 1, 3. Because we weren't including the endpoints of the interval, I will put parentheses to make sure we don't include those two numbers in our solution. So this topic was a difficult one to explain. I hope the tutorial was helpful, and as always, I wish you the best of luck.